That was milk buckets. Then we'll move to supervision. We have a sequence or maybe line with people of two or cows of two types, coaches and campers. I think I will say coaches and students because it will be easier to hear what I'm saying. So we have a line. The students I will mark with just white. And the coaches I will use another color for. So coaches will be with this color. And there is also some range, the range D. Every student needs to be, there exists a coach within D units to the left. So student is happy if within D units to the left, there is at least one coach. Then it's a good situation. We need to count the number of subsets of people or subsets of cows that are good. That is, every student that goes is satisfied. So at least one coach is there in the input. I actually first misunderstood the statement. I thought that this range goes in two directions. That's what I implemented. It didn't work for the sample test, but turns out that the fix, once I realized the fix, it was few characters. Luckily for me. Okay. N is up to 1 million. I think there was subtask with N up to few thousand as well. So N squared allowed partial points. There was also stupid subtask with D equal to 0, but let's ignore that. And for our convenience, the values were distinct and already sorted. And that's it. Okay. When we have a line and some satisfaction condition about ranges, one possibility is to think this way. For a student, if I want to take it, then also I need to take at least one of those coaches. So there is some kind of implication. Sometimes this kind of graph-like analysis leads to solutions like 2SAT, but that's not the case here. It would be very slow, or it wouldn't work at all. Also, 2SAT cannot do counting. 2SAT can check if there is a solution. It cannot count usually. So that's not the way to go. What I can do is I can go and for every person decide if I take it or not. And after I kept making some decisions, I can remember something about those decisions to know if the next person can be taken or not. That can give you idea for inefficient solution. dp of I, the index in this sequence of people from left to right. And then what do I need to know for this next student to be taken or not? I need to know where is the previous coach, last coach. So it's n squared states. I can have this dp. What is the number of such possibilities or subsets being taken in the prefix up to index I? So that this would be index of the last coach taken. For every next person, if it's a coach and we take it, then we also replace this dimension. If it's a student, we can take only if the last coach position plus D is greater or equal than this position. And that's it. Very easy transitions. O of n squared time and memory will get partial points. Sadly, it's very hard to improve this because of the number of states. We already have constant transitions here per state, so yeah, this is not good. We need to have dp of I or dp of last coach. We cannot have time complexity better than the number of states in our dp, so that's not a good way to go. dp of I also I think is not good enough unless you maybe define it properly. That is, I don't think it's easy to phrase what we should represent dp of I for any arbitrary index I. Like it matters what was exactly the last coach taken. So when I was solving this problem, I went for DP of last coach. For every coach, I said, what is the number of solutions so far if I also take this coach? And this coach I know allows me to take the next few students. And then I can iterate. If this is the state, then I move to the next state. So I move to the next coach to be taken. So a quadratic solution, let's talk about solution in O of n memory, O of n squared time. Quadratic solution for every coach iterates what is the next coach taken. From I to j. And as I jump, I need to process students that are in a way. I know that coach allows me to take the next students within the distance of d and nothing more. So I can ask some separate data structure, maybe in logarithmic time, maybe in constant time, what is the number of students here? And whatever the count c is, the 2 at power c, 2 at power c is the number of ways I can choose students in between of ij. Also, I and j might be very close to each other. So if I transition from this I to this j, I only ask about the number of students within this range in between. So I transition from dp of I to dp of j. I and j are indices of coaches. And I do something like this, dp of I multiplied by power of 2 of something. Like this is a count. Count of students between of coaches I and j that are within range of coach I. Those are the transitions. And always when I finish, for every dp of I should consider possibility that this is the last coach. Then the answer should be increased by 2 at power the number of students here. Or alternatively, you can make some implementation trick. You can add a coach, one extra coach at infinity. Infinity should be far enough that the d distance is not enough for any student. And you say that the last coach taken needs to be this one. Then the answer will be simply dp of that last guy, last fake coach. -1 because you don't want to count. The statement said we cannot count empty set. Though it depends on implementation if you will need this -1. If you have -1, be careful to use modulo properly. When you apply modulo operations, this doesn't work because it can give you negative value. Negative values don't modulo nicely in C++. You need to do it this way, to subtract 1. How much time we have? Not much. Okay. Now, to speed this up, I'm going to, this power of 2, I want to quickly sum up a lot of states. So for dp of I will transition to a lot of dp of j's, automatically telling them what power of 2 they should use. That is, if I have coach I here, then there is a distance of d here. I can just once, for the coach d, count the students that are here. Let's say there are 5 of them. And then all the j's that are in this range, all the j indices, should be increased by the same value. dp of j plus equal dp of I multiplied by power of 2, the 2 to the power 5. Very easy. Am I right? Am I saying something stupid? No, it's okay. Of course, with modulo operations. This kind of addition of a constant you can do using segment tree add or using prefix sums or running sums. What I did is running sums. That is, I only added the value at this position, at this index of a coach. Maybe I used lower bound, I don't remember, or you could use 2 pointers. So I find for every I find the first coach that is after d units. And at that coach position, I increase it by this much. And I let running sums do the job. That is, as I keep going forward, this value will be propagated forward. So I actually here say running of j plus equal this, where j is the first index j after d units. And then as I keep going, always running of j plus equal running of j minus 1. Okay, that is how to handle transitions from I to far away j. The second type is that I need to handle transitions from I to j that is close, within the d distance. Then what is the formula? From dp of I to dp of j, I will transition, and I need to increase it by the number of students in between. And that depends on both I and j. But the nice way is to phrase it in terms of I and j, so that we could express it as a formula that splits into something dependent on I and j, and then we can optimize it, is that it's the number of students here. If for every coach you know the total number of students in the prefix up to it, so we define student prefix of I, number of students before coach I. With this definition, the number of students before I and j is easy. It's student prefix, or let me just say spref. Spref of j minus spref of I is the number of students in between. So 2 needs to be raised to this power. And if I need to say this, dp of I multiplied by 2 to the power of this, very common trick in harder problems, especially Platinum, and something to do with summation or even FFT, which is ICPC topic, is you get rid of brackets or you split into separately I and j indices. So this I will express as 2 to the power that divided by 2 to the power this, right? If you multiply something by times 2 at x minus y, equivalently you multiply by this and then you divide by 2 at power y. That's the same. So actually this becomes dp of j plus equal dp of I times power of 2 of s pref of j, and then divide by power of 2 of s pref of I. Yep, I will now group by index. So what I can do is when I'm at index I can compute this value, which depends only on index I. So given I can compute the highlighted value. It's a constant based on I. And for everything in this range, again, I can use segment tree or I can use running sums to add something in constant time to a range. To everything in this range, I tell it, I need to add to your dp this value multiplied by this value depending only on you. So to the range, I say I add this constant. It's like running sums my number 2 of this range. This is pseudocode plus equal this thing. Here I use modular inverse. I can pre-compute inverses of 2. So this can be constant time here. I do this. But as I keep going, then for every future index, what I do is dp of I or dp of j, whatever, plus equal running 2 of I multiplied by this missing thing. So I know somebody earlier told me to increase myself by this constant, depending on that old value, multiplied by something depending on my current index. So when index 4 tells something to index 7, actually index 4 knows this value. So this yellow value is added to everything here. And when I get to index 7, I take this value that was added to me and I multiply it by this new value that I know now because it's based on me. Okay, that's how you can solve it. I will again show for a moment my code, but I will not go for it. And what was the name? Was it Supervision? Yes. 100 lines, including the comments. So not that fast. I think that can be better, but you can look at this part, I guess. Yeah. Again, later you can rewind and study it more. What I did first is because I thought that coaches go in both ways, I actually changed every coach into a range. I numbered students by indices from 0 to the number of students minus 1. Every coach, I computed the range of student indices that is covered, and then I focused on those ranges. I forgot about positions of students and coaches. And then I have here something that is, you're given a lot of ranges, you need to compute how many subsets there are of ranges and then things inside of ranges. And here I transition between ranges, but it boils down to the same thing. I implemented in n squared multiplied, in O of n multiplied by lower bound. I don't know why this says n squared, some old piece of code. Yeah, so it's n multiplied by lower bound. What's the similar problem score level on code forces that can practice? 2400? Maybe less than that. I'm not good at difficulties in code forces, maybe 2300. There is a website for that and you can look it up later, but it's not there right now. Codetiger.me. Codetiger.me. There is this website that estimates difficulties of USACO problems, so maybe in 1 month you will see the difficulty of that problem. 23 would be very hard gold problem. I wouldn't say that was that hard, so maybe 2000 plus a little bit. Anyway, you need to study DP counting problems, and you will encounter something like this. Any other questions? Yeah. I also had a bug which was related to, I think, some ranges being empty. So if you keep getting wrong answer, it might be because of that.